Pits offer equally loud two-tone sound. Formula as before. Case 3 if H1 and if H2 have an harmonic relationship. This is the third case. If the absolute difference is n times the fundamental frequency, where n is an integer and f0 is within the musical pitch range. Same pitch as a pure tone at frequency f(h1) minus f(h2), but with brighter timbre klang. So we can hear it. The blue one is a complex tone from 8 to 1000, and pure tone has a frequency of 200. The complex tone is it is 800 Hz and 1000 Hz. So and the difference is 200. We can just listen to this. It's 800 Hz, 1000 Hz. Yes, and pure tone. Okay. Yes, we see the complex tone has a frequency. Should try to find out here. The pure tone is easier. Pure tone has a frequency of 200 Hz. It's from here to here, and here and here. It's from 001 to 005 here. Yes, and 0011 and 0016. That gives sense. That makes sense. I try to explain the complex tone. There's 1 peak, 2, 3, 4, 5 peaks here, and then or you can say 1, 2, 3, 4, and number 5, and the distance between those two peaks here are the same. It's 0.005 second. This distance here in time from here to here is the same as from here to here, and here to here, and so on. Yes. Okay, pitch offer equally loud tune sound. Same formula, but there are no harmonic relationship. Yes. So I think it should be case no harmonic relationship. Absolute difference between f1 minus f2 is n times f the fundamental frequency. That confused me a little bit, because it should be different from n times fundamental frequency. Yes. Okay, no, that's true. Absolute difference is n times the fundamental frequency. N is still an integer, but f0 is outside the musical pitch range. Up here it was inside the musical pitch range. Again, careful. We have the pitch is ambiguous and inharmonic. We have pure tone at 520 Hz and plus pure tone on 620 Hz. And the fundamental frequency of 20 Hz. Sounds strange. The difference between F1 and F2 is 100 Hz and the FÖ is 20 Hz. So it's outside the musical pitch range. We have here the blue tone from 520 to 620 and the pure tone with 100 Hz. This one from here to here, 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 here. This is a pure tone with a frequency of 0.001 second. No, 0.01 second. One divided by 100. 0.01 second. Like this. The blue complex tone has a much bigger frequency and a much smaller what's called period. Actually, pitch of an harmonic sound, Fn, is n times the fundamental frequency. Pitch of an harmonic sound. A harmonic sound is composed of frequency components regularly spaced. Fn is n times Fö. F1, F2, F3, F4, F5, F6, F. On the temporal domain, its waveform repeats regularly with a period T is 1 divided Fö. Yes. The amplitude of each component has only a minor impact. The amplitude of each component has only a minor impact on the pitch. The first harmonics can be omitted. Then we're talking about missing fundamentals. So we have some here. Waveform here, Y is this 2 times. Here is 2 in sinus A1 sinus 2 pi times ft, and then a sinus 2 pi times 2f, and then 3f, 4f, 5 and 6f frequencies according to this f2, f3, f4, f5 and f and 6f. And this is the frequency. No, this is the period for the harmonic, this one. And we see again the amplitude of each component has only a minor impact on the pitch. From the sense of hearing, we have some harmonics here, waveform with a frequency of 200 Hz plus a wave of 400 Hz, 600 Hz, 800 Hz, 1, 2, 3, 4. And if you put them together, we get this waveform with a frequency of 200 Hz as a fundamental. But it's from here to here. It's yeah. So I told you this is 5 milliseconds from here to here. And that's 1, 2, 3, 4. 1, 2, 3, 4 peaks. So it's it must be 1 point. The period from here to here is 1.25 milliseconds. So if we omit the first, the fundamental frequency, we get 2 plus 3 plus 4, 2 plus 3 plus 4, and then this waveform here, and still the period on 5 milliseconds. An illustration of how a complex tone can be made by adding together pure tones at harmonic frequencies. The bottom panel shows the effect of removing the fundamental component. Then pitch of an inharmonic sound. Fn is n times Fö. Or it should be different from this. I think this is a bad signs here. pitch of an inharmonic sound. Different pitch can be heard. Usually the pitch is induced by the most salient component. We have here a glockenspiel at C6. I don't know what this is. Pure tone at 1047 Hz and pure tone at 5656 Hz. Yes, okay. Now we listen. Glockenspiel. Yes, it's just one this tune, this sound. The next one, pure tone at 2007. Here, two is 1047 Hz and then 5656 Hz. Yeah, there's not a regular relationship between those frequencies. 5656 Hz is about 5.5 times 1047 Hz, but it's not a natural number. Pitch of a narrowband noise. A narrowband noise can have a clear pitch only if it has a weak peak. Clear pitch only if it has a narrow peak. Its pitch can be predicted by the region with the most energy. The percept is often recognized as spectral pitch. Here the narrow blue one, narrow noiseband, and we have the red one is sinus to 400 Hz. Sinus 400 Hz. Now we listen to the narrow band noise around 400 Hz. Again. And a pure tone. Okay, there's some differences. The dimensions of pitch. Illustration. Is it the same tone height? Was the second note of the melody played with a higher, a lower, or the same pitch than the first note? So pitch is the definitions of pitch is following. According to the sense of hearing, pitch, that aspect of sensation whose variation is associated with musical melodies, the perceptual correlate of repetition rate. And from the PowerPoint definition of pitch, pitch is that auditory attribute of sound according to which sounds can be ordered on a scale from low to high. So illustration, is it the same tone height? Was the second note of the melody played with a higher, a lower, or the same pitch than the first note? So, then there's a program Socrative on your phone or laptop. Log in as a student. Join the room. DTU music. Now I listen to this.